Yeah. For our next guest, I have come up with, you could say, something special because I put all my creativity together. So, dear Sebastian, here is my poetry pitch for you. Sebastian Pöplau is a very smart PhD. In his research, he focuses on sophisticated techniques which enable software that is secure and bug-free. When away from computers, he enjoys fencing, climbing, and sailing on the sea. Today, he introduces symbolic execution. Symbolic, excuse me? So this present testing technique is new to you and you don't yet understand? Don't worry, Sebastian will show you how it can complement your software testing. He will further discuss compilation-based symbolic execution, a technique that enables symbolic executors to be relatively fast. But now, enough of the poetry. Sebastian, would you like to start?
Beautiful, Paul. Thank you very much for the introduction. Is my audio fine?
You're welcome.
See the slide?
Yeah, we can hear you. Yeah, everything is working fine.
Perfect. So, hi everyone. Welcome to my talk. My name is Sebastian Pöplau. And as you've just learned, until recently, I worked at Eurcom, which is a research institute in the south of France. And in this talk, I hope to, after an introduction to symbolic execution, convince you that it is a great complement to fuzz testing. Excuse me. So it turns out many people have not heard about symbolic execution before. So I will start with a general introduction, what it is, what it's useful for. And then we proceed to some research projects that we performed recently to improve the performance of symbolic execution. So the initial idea is actually quite old. The first paper on symbolic execution is from the 70s. But at the time, technology and also algorithms were not sufficiently advanced to implement practical systems. So it took some time, and in the 90s, there was some significant progress in a research area that is very important for symbolic execution. So starting in the 2000s, we saw some first more or less practical systems. And then in recent years, they have found their way from research prototypes into actual applications in the industry. And in case you're wondering where this thing is used at all, we've heard earlier that Microsoft actually uses it for testing the Windows kernel. And it's also an important part of Clang Analyzer, the static analyzer of the Clang project. So there are places where it's used, but it's not very common for people to get in touch with it directly. So let's start with an introduction. What is symbolic execution? The core idea of symbolic execution is that we keep track of how each value in a program is computed during the course of execution, so that later we can reason about those values. And to illustrate the concept, let's look at this example program that just performs some arithmetic and then checks two conditions on the inputs and on derived values before it hits some error condition in one of the branches. Now, suppose we wanted to perform symbolic execution of this program to find the bug that is marked with the error comment. What a symbolic executor would do is it would walk the program instruction by instruction and trace all the computations as they happen, so that when it hits this conditional, the first conditional, x equals 100,000, it knows which constraint has to be met for the program to take either branch out of the if. Now, suppose we wanted to take the else branch, then symbolic execution would trivially derive that x needs to be some value that is not 100,000. And in the example on the right, in the execution tree, you can see that x equals 0, y equals 0 would be one possible solution. That is, symbolic execution gives you input values, in our case, input values for the function we're testing, to reach all possible paths through the program. What is more interesting is the then branch. So if x is equal 100,000, then we hit the next conditional, which checks the condition that x is less than z. Now, note that z is not an input to our function. It is a derived value that we computed in the first instruction of the function. So here it is important that symbolic execution keeps track of how each intermediate value is computed as it walks through the program. And based on this knowledge, it can now express the condition in terms of the input values, and it can derive solutions that take either branch out of the if. So for example, if we wanted to hit the error condition in the tree, you can see in the lower right corner, there is a solution x equals 100,000 and y has one value that makes the second if condition true. If we compare this to fuzzing, we will do a much more detailed comparison later. A fuzzer in its most basic form just randomly mutates inputs, right? So we would start with two random integers, x and y, and mutate them. But it would be very hard for a basic fuzzer to meet, for example, the condition x equals 100,000 with random mutations. Modern fuzzers are much smarter. So to a certain extent, they can handle such conditions. But you can see how symbolic execution is made to more accurately reason about the flow of data through a program. Now, I've shown you that based on the conditions that we derive from the if statements, we can actually find new program inputs. And the way that symbolic execution does so is by means of a piece of software called SMT Solver. And before we get into what SMT solvers exactly are, let's look at the example on the right, which represents the interaction between symbolic execution and the solver for the concrete example from the previous slide. So the symbolic executor would tell the SMT solver that in our concrete scenario, there are three variables x, y, and z, all of which are 32-bit vectors. And it would then communicate the three constraints that we found. So z was computed as 2 times y. Also, to take the branch that we are interested in, x needs to be equal to 100,000 and x needs to be less than z. Based on this information, the SMT solver is now able to first determine if there is a solution to these constraints. That is, if there is a set of inputs that makes them true, and also give us one set of such inputs. So the solver generates the inputs that we are interested in that will eventually take the program down the branch that we asked for and hit the bug that we were looking for. So most implementations of symbolic execution use SMT solvers in one way or another to derive new inputs into programs. This is what symbolic executors use where fuzzers would employ random mutations. In case you've been wondering, SMT, the acronym, stands for Satisfiability Modulo Theories, which is a theoretical framework that allows us to express and solve queries in logic and arithmetic settings. And that is very useful for symbolic execution in the end. SMT solvers are based on heuristics for the Boolean satisfiability problem. If you've had the pleasure of dealing with theoretical computer science at some point during your career, you will recognize this problem. It's actually the first problem that was shown to be in NP complete. But all this is just to say that SMT solving is extremely expensive. So having the solver find a solution to a given set of constraints is an expensive operation. And of course, that has an impact on symbolic execution as well. So now, as promised, let's do a more detailed comparison of symbolic execution and fuzzing. First of all, speed. We've just seen symbolic execution is expensive, which usually translates to it is slow. Whereas I hope the talks we've seen so far have convinced you that modern fuzzers are really, really fast. As an example to illustrate this point, most fuzzers execute the target program hundreds to thousands of times per second, whereas symbolic execution often measures its performance in the number of seconds it takes to execute a program once. So there is quite a difference in terms of performance. On the other hand, if we look at the reasoning power of symbolic execution and fuzzing, we find that here the situation is the other way around. So fuzzers in their most basic form just perform random mutations, and so they don't do any sort of elaborate reasoning about what is going on in the target program. Modern fuzzers, yes, apply clever tricks, but still the basic idea is that a fuzzer, in order to achieve the high performance that it usually has, cannot reason deeply about what is going on in the program. Symbolic execution, on the other hand, uses the expensive SMT solver to reach even the most hidden parts of target programs. In exchange, it is relatively slow. So now, of course, the relatively obvious idea is, why don't we combine those two? This is often called hybrid fuzzing, and there are some research implementations that work quite well. These are prototypes that have been published in scientific conferences, so they are not products, but they're really worth looking at if you're interested in the topic. In particular, Driller and QSim are quite interesting. So let's talk a bit more about the performance of symbolic execution. As we've seen, performance is the main challenge for symbolic execution. And we've seen that one core factor in the slowness of symbolic execution is SMT solving. But it turns out there is a second aspect. And this aspect is tracing computations. We've seen in the initial example that symbolic execution keeps track of each computation because it needs to know how each value in the program is derived. So it has to be aware of each computation that goes on in the program. And it turns out this is really expensive. I will first show you how traditional implementations of symbolic execution perform this tracing. And then we'll have a look at an idea that we recently implemented that leads to a faster approach. So traditionally, symbolic executors do what we call the interpreter approach. The program on the left is another example program, this time represented not in C code, but as LLVM bitcode. Bitcode is a representation that is somewhere between high-level programming languages and machine code. And it's actually the representation that, for example, the Clang compiler uses to reason about your program when it optimizes. There are various technical reasons why many symbolic executors choose to use such an intermediate representation as the basis for their execution, but we won't go too much into that. What is important is that the program, the target program, is available to us in this form. And now our goal is to execute it symbolically. That is, we want to execute the program, but also keep track of all the computations that happen inside the program. Now, typically, the way this is implemented is in the form of an interpreter that loops over the instructions of the target program. So it repeatedly fetches the next instruction from the program. In the case of our example, the first instruction would be number 3, SHL, which is for shift left. And now what the symbolic executor would do is first it would compute the actual concrete result of the operation. So a left shift is just computed as a left shift at the C or C++ level. But also, and this is unique to symbolic execution, it would build an expression. So it keeps track of the fact that the result of this operation was computed by means of a left shift operation. So that later, if the result shows up in some branch condition, we know how to trace it back to the original inputs of the program. It turns out interpretation is really slow. We know from experience with programming languages that interpretation is typically not the fastest way to run. And we also know that a faster way is compilation. So the idea for our project was, why not apply the same thing to symbolic execution? What we built is a symbolic executor called Simcc, for Symbolic C compiler, which applies the idea of compilation instead of interpretation. And to illustrate how it works, we're going to look at the same program again. So this is the exact same example program, but this time Simcc works at the compiler level, meaning that it hooks into the compiler, and while we are compiling this target program to machine code, it modifies by inserting additional instructions. So here you see that we inserted 2 blocks of instructions, while the middle part is still the original program. What we inserted is calls to a runtime support library that inform the symbolic executor about each and every operation that is going on. So we tell the support library that we are shifting, we are comparing whatever happens in the program. And the important point here is that all these instructions, the original instructions, as well as our calls to the support library, in the end get compiled down to machine code, which means that they run a lot faster than the interpreter would normally work. Also, what is important is that Simcc performs this transformation once. When you compile the target program, it inserts the instrumentation, whereas an interpretation-based symbolic executor has to perform work every time you execute the target program. Let's briefly discuss how this is implemented. As you've just seen, there is a compiler pass and a runtime library, and the pass does what we've just seen in the example. It basically inserts instructions into the target program that call the runtime library when we execute the program and inform it about all the computations that happen during execution. We built this pass on top of LLVM, which means that we can integrate easily with each LLVM-based compiler. The first that comes to mind is Clang for C and C++, but then it turns out that for many programming languages, there are either the canonical compiler is based on LLVM, such as for Rust, or there is an alternative compiler that uses LLVM. For example, there is Go LLVM for the Go language. The second part, the runtime library, is responsible for keeping track of computations, keeping a record of how each intermediate value in the program is computed from the initial program inputs. And also, it is where we interact with the SMT solver. So whenever we hit a conditional statement, a branch of some sort, we call out to the solver and ask it to generate new program inputs that would make us take another way out of this condition. For this, we just reuse code from QSim. QSim is what I mentioned earlier, an existing symbolic executor that is known for its high performance. And since this interaction with the solver is not the focus of our work, we just reused their excellent code. So let's recap quickly. We've seen that symbolic execution has most definitely a performance problem. And there are 2 core factors that influence the performance of symbolic execution. One is SMT solving, and the other is tracing computation. And with Simcc, we try to address the second problem by compiling symbolic execution into a target program instead of using the traditional interpreter-based approach. Now let's look at a bit of an evaluation. Does all this actually work? What we did to evaluate Simcc was we compared it with QSim. QSim has been the gold standard in symbolic execution performance for the past 2 years because it's really fast in comparison with previous systems. And we measured the code coverage over time in comparison with QSim on 3 popular open source projects. So down in the figure, you see OpenJPEG, LibArchive, and TCP-DUM. In both cases, for Simcc and QSim, there is a fuzzer, AFL, running alongside symbolic execution. So this is hybrid fuzzing. We exchange samples between them. So whenever AFL generates interesting new inputs, we pick them up with QSim or Simcc. And when QSim or Simcc produce interesting inputs, they are fed back to AFL. I don't have them in the figure here, but if we plotted the coverage from pure AFL, it would be lower than QSIM. So QSIM already improves on the raw fuzzing approach. And then we showed that Simcc achieves higher coverage on top of that. Now, what is interesting and attests to the utility of hybrid fuzzing is that even though OpenJPEG is heavily tested and routinely fuzzed by Google in OSS fuzz, we found two vulnerabilities in OpenJPEG. Both of them are writing heap buffer overflows, so they are likely exploitable. And also, what is interesting is that we found the difference in coverage correlates with the difference in speed. So you can see on the 3 projects that we tested, the advantage compared to QSIM is different. And it turns out that this difference is correlated with how much faster than QSIM we are. So this supports our intuition that making symbolic execution faster actually gives us more coverage when using it in hybrid fuzzing, which then hopefully translates to more bugs found. Now, to conclude, I hope I have convinced you that symbolic execution and fuzzing go together really well. The strength of each complement the other. And with Simcc, we have recently shown that symbolic execution can be made a lot faster than with traditional ways to implement it, hoping to contribute to making symbolic execution more practical for industry applications as well. If you have questions, of course, feel free to ask now, but if anything comes up later, feel free to send me an email. And also, if you're interested in Simcc, all the code is publicly available. You will find documentation and also a link to the research paper on the repository. Thank you.
Yeah, thanks, Sebastian. Indeed, there are some questions. One participant wants to know if you have comparison metrics with other LFVM bitcode-based symbolic executors, like, for example, CLI.
Yes, absolutely. So before doing Simcc, we actually ran a sort of comparison study of multiple symbolic executors, including Anger, S2E, and CLI. And first of all, it turned out that QSIM is indeed a lot faster than those other 3. But also, the reason why we didn't add CLI to the comparison in our Simcc evaluation is that CLI has problems when it encounters instructions that it doesn't know. So this is a bit technical, but if you try to analyze a program with CLI that contains things it doesn't understand, it just refuses to work altogether. So for using it on real world software, there are certain issues. You have to be very careful about choosing the software and how to build it. So we were not able to use it in our evaluation.
Thanks. Another participant would like to know about the difference between concolic execution compared to symbolic execution.
Yes, I didn't go into that in the presentation too much, but the basic idea is that classic symbolic execution would explore all execution paths through a program. So in our initial example, you remember the tree of possible execution paths through this program, and symbolic execution would explore all of them. Now, in this scenario, you have to, of course, prioritize, because often the time budget is not enough to explore all paths. And you run into a problem where you have many paths because they double with each conditional, which is called path explosion. So people have come up with this idea that instead of exploring all paths at once, what you can do is use one concrete input, an input that would give you one path through the program. And then only at branch points that you hit during this one path, you ask the solver for alternative inputs. So concolic execution is the idea that we execute along one given path and generate new inputs at each branch point. And it turns out this is a really good fit to avoid path explosion and also to work with fuzzers, because we can now take our concrete inputs from the fuzzers. We just take inputs that the fuzzer considers interesting and promising. We run concolic execution on those, and this gives us new inputs that just branch off from this predetermined path at some point. And these new inputs we feed back to the fuzzer.
Okay, thank you for this comprehensive answer. Another question is, how much time was spent on the execution interpretation as compared to SMT query solving in your benchmarks?
This is very interesting. I would have to look it up. We have, so if you're interested in the precise numbers, we have them in the paper. It depends a lot on the program you analyze, actually, because some programs, for example, imagine a program that hashes something or that performs cryptographic operations. They are super difficult to analyze with SMT solvers. So there you will spend 99% of your time on SMT solving. While in other cases, typically the cases where fuzzers also perform relatively well are where you don't have such expensive operations. And then execution becomes a larger part of the analysis. And those cases are where we actually gain a benefit. Obviously, if all the time is spent on SMT solving, then Simcc with its faster execution component doesn't buy you anything. But there are a lot of cases where execution is an important factor. But again, for the details, I refer to the paper. I don't know them off the top of my head.
Maybe you can post a link in the Slack too, so there's a direct connection then.
No problem.
Yeah. So one more question, and then we will do the break. Another question was if you implemented an improved version of QSIM in the Simcc, or is that completely different from QSIM?
There are two parts. So symbolic execution typically has the execution component where you trace operations, and it has the reasoning component where you interact with the SMT solver. The reasoning component we take completely from QSIM. We do not change anything. The execution component is a complete re-implementation. So basically we just pick the parts from QSIM that we are not interested in improving, and we re-implement the execution. So for context, the way QSIM works is not interpreter-based. It is actually a relatively interesting, different approach. It works like a debugger. So it uses Intel pin to attach to the target process from the outside, and that way it observes each executed instruction. But it turns out, while this is a lot faster than traditional interpreter-based approaches, it is still slower than our compilation-based technique.
Okay, great. Thanks, Sebastian. Also, the participants who asked the question, thank you in the chat for your answers.